Hello students, now I take the speed of sound in different mediums. Sound waves in different mediums. Different mediums. You know that sound waves are longitudinal. The sound waves longitudinal waves in gaseous medium in solids and liquids. These waves may be longitudinal and transverse So let us take first in the solid mediums. The speed of sound in solids. This is V equal to square root of y upon rho, where y Young modulus rho density of solid. This is now suppose we have taken the solid, so we denote it by Vs. The speed of sound in liquids and gases. This V equal to square root of K upon rho, where K, it is the bulk modulus, and rho density of medium. And you can see that the value of Young modulus is very high. So this speed is very large. So in solids, the speed of sound waves is more than the speed of sound waves in your liquids and gases. the speed of sound is more in solids than in liquids and gases. So now we take about the gases. We are having the work modulus. And in gases we are having the two main formula of this speed of sound. Newton's formula. For speed of sound in gases. There are compressions and rarefactions in medium in gas medium, because the waves are longitudinal. Waves are longitudinal. Newton assumed Newton said that there is isothermal change in gases, in gas medium during the propagation of the So isothermal change means that what that in at the point where the compression is there, the temperature increases, and the rarefaction there the temperature decreases. So what the temperature increases in the compression, that the same amount of the temperature is decreased in rarefaction. So thus the temperature of the medium remains the constant. So there is the isothermal change during the propagation of this longitudinal wave. So we have this PV equal to constant. Using Wiles law, PV equal to constant. So now we have this P dV plus V dP equal to 0. We have differentiated to this one. So this is now your P dV equal to minus V dP, or we can have this P dV upon V. This is equal to this P is equal to minus V dP upon dV. So this P equal to minus dP upon dV upon V. So this is what the definition of the bulk modulus. Change in pressure upon the, this is the your stress, and this is the strain, this is the volume strain. So this is equal to K, the bulk modulus. So now we have, therefore, the speed of sound V equal to square root of K upon rho. So now we have this square root of P upon rho, where K is equal to P. This is the equation given by the Newton. At NTP, this V is equal to 280 meter per second, but experimentally V equal to 332 meter per second. So the speed of sound given by Newton does not match the experimental value. Therefore, it needs some correction. Then there is the Laplace correction. Laplace correction. According to Newton, speed of sound in case this V equal to square root of P upon rho. The value of speed of sound in air does not match with with experimental value. So Laplace made some correction. Known as Laplace correction. Laplace correction. According to Laplace, the temperature of medium does not remain constant because gases are bad conductor of heat. So there is adiabatic change in medium. Now adiabatic change, the equation of state. For adiabatic change, PV gamma equal to constant, where gamma equal to Cp upon Cv. Now we differentiate to this one. Differentiating, then this is your P gamma V gamma minus 1 into dV plus dP into B raised to power gamma is equal to constant. So we are having this P gamma V gamma minus 1 into dV is equal to dP into B raised to power gamma. So now we can have this gamma P is equal to minus dP into B raised to power gamma upon B raised to power gamma minus 1 into dV. So now this gamma P is equal to minus dP. Now this B gamma will cancel and this will be B minus 1. So we can have this dV upon B. So this is again equal to the bulk modulus K. This is equal to gamma P. K bulk modulus. Bulk modulus. Therefore, the speed of sound V is equal to square root of gamma P upon rho. This is now formula. Now if we apply this formula for air at NTP, V equal to square root of gamma into square root of P upon rho. So this is equal to square root of 1.4 and this is now 280 for air. For air, gamma equal to 1.4. So this is your 331 meter per second. This is now P. Now this value is very close to the experimental value. This value of V is very close to experimental value. Therefore, this is the right formula for the speed of sound in the gas medium. So, this is what the correction made by the Laplace, then that of the Newton. Newton supposed that there is also thermal change, the whatever energy or the temperature is produced at the time of compression is same. The same temperature is lost at the time of rarefaction. So temperature of the whole of the medium remains constant. But Laplace said that this does not take place because the gases are bad conductor of heat. So whatever heat is produced in the compression is not the same as the heat absorbed in case of rarefaction. So temperature of the medium does not remain constant. So there is the adiabatic change in the medium. And then he applied this formula and found that whatever this is given, this is the right one, that matches with the experimental value. So these are the speed of sound in the different mediums. So you all like, share, subscribe this video, and also I tell you note online classes from June 1st, 2021 and 7014734805. So this is for both 11th, 12th and NEET. So you all like, share, subscribe this video. Thank you very much.